Welcome, everyone. This is our last seminar in the seminar series this semester. It's a great pleasure to have Arkya Chatterjee to tell us about his new work. Arkya is a PhD student at MIT, supervised by Professor Xiaogang Wen. I noticed Arkya's work, I guess when he started doing his PhD, he already did very impressive work with Professor Wen on non-invertible symmetries. And during his PhD study, he has been working on this direction and also expanded his scope to other directions like quantum criticality and so on. Today he's telling us about his newest result. Welcome.
Thank you, Lucian. Thanks for the invitation. Thanks for the very generous introduction. And thank you everyone for coming to my talk. Today I'm going to be telling you about some work that I did with Sal and Shuheng, who are both at MIT. Sal is a graduate student, Shuheng is a professor there. And we put out this work 2 months ago now. The archive number is here. So the work is about realizing certain symmetries of field theories in a lattice model. And I kind of truncated my title a little bit. It was too long to put on the slide. Um, so yeah, I'm going to be telling you about how the so-called axial charge of a massless Dirac fermion in 1 plus 1D um, and the related chiral anomaly um, is realized in a lattice model. Okay, so let's get started. Um, so part of the motivation comes from trying to realize a lattice gauge theory, in particular the standard model in a finite lattice where you can do concrete non-perturbative calculations. And this is an approach that was pioneered by Wilson back in the 60s or 70s. And a longstanding challenge in this field is in the field of lattice gauge theory is to try and realize so-called chiral symmetries of fermions on the lattice. What do I mean by chiral symmetries? I mean these are symmetries that act differently based on whether the fermion is left-handed or right-handed, loosely speaking. Um, So this is an important question for particle physics because the standard model of particle physics is a chiral gauge theory. So if you wanted to do any calculations on a lattice that reflect the real world, you would need to be able to realize chiral symmetries and then gauge them. And there's a related problem of fermion doubling, which has a long history. For instance, back in the 70s, people came up with a staggered fermion model, which tried to kind of address this problem of doubling the number of fermion modes when you put them on a lattice model in a finite lattice. And people tried to also use other kinds of models, models which were not completely local, by modifying what you mean by a derivative when you put a field theory on a Euclidean lattice, Euclidean space-time lattice. There are also other ideas motivated by coupling to SPTs in one higher dimension and a related idea of symmetric mass generation. There's many other proposals for trying to address the problem of realizing chiral fermions and chiral symmetries of such fermions in a lattice model. And so our work kind of addresses this question in a very simplified setting. I should also note that most of the work on this chiral fermion problem has gone into like dynamical aspects where people are trying to come up with some kind of Hamiltonian, some lattice action, which has a single chiral fermion or an odd number of chiral fermion modes in some low energy limit. Our work addresses the kinematic aspects of the question, namely trying to realize the symmetries and anomalies of such fermions. Another motivation comes from kind of a condensed matter point of view, where anomalies we know now, provide a lot of many non-perturbative constraints on infrared physics. There are many examples of this. Some illustrative examples are, for instance, anomaly enforced obstruction to trivial gapped phases in 1 plus 1D. Um, there are so-called LSM-like Liebschulte-Mattis-like theorems in both in 1 plus 1D and higher dimensions, where they involve mixed anomalies between internal and lattice symmetries. Symmetry fractionalization in so-called symmetry-enriched topological orders involve a mixed anomaly between an ordinary zero-form symmetry and a higher form symmetry. Um, and yeah, so this kind of tells us that it's interesting to realize whenever a UV microscopic model has certain anomalies. And um, if you once you've identified such a structure in the symmetry, you can kind of get various constraints on the infrared low energy fate of that model. So one of the questions that we're also addressing here is, is it possible to realize an anomaly of continuous symmetries in a Hamiltonian lattice model, which has a finite dimensional Hilbert space, like a spin chain or single fermions on each lattice site? Um, and the reason to ask this question is typically when you look at anomalies in the condensed matter context, most of the lattice realizations are of anomalies of finite symmetries. So it's interesting to ask uh, whether such whether the analogs of those for continuous symmetries like U1 can be realized in a finite dimensional Hilbert space. So these are the two rough motivations. And before I get into the meat of the talk, I want to kind of give away the punchlines a little bit so that if you don't follow the rest of the talk, at least you remember what the main takeaways are. So we're going to explore these questions in the context of a massless direct fermion field theory in 1 plus 1 dimensions, which means one space and one time dimension. This field theory has two U1 symmetries that go by the name of vector and axial. And there's a mixed anomaly between them. I'll elaborate on what that means. This mixed anomaly goes by various names. It's often known as chiral anomaly, also known as Schwinger anomaly after Schwinger, who first identified this. So we'll realize both of these symmetries exactly in a simple lattice regularization um, of this field theory. As I said, there's no fancy lattice model here. Really, the key result is in the kinematics of the symmetries and anomalies. We'll see how the lattice symmetry matches the anomaly in the continuum. This is something we learn when we learn about anomalies. Is that anomalies are RG invariants. So if you see an anomaly in the infrared in the continuum field theory, there must be a way in which that it's matched in the UV or in the microscopic modeling. So we'll address this question along the way, and in the end, we'll find a novel kind of gapless constraint arising from the lattice symmetries, which will be reminiscent of the kind of constraints that anomalies give in the continuum field theory. Yeah, so let me stop here and see if there are any questions about the motivation or just the summary that I've given so far.
I have a question.
Yeah.
Suppose now infinite dimensional Hilbert space, do people know how
Mhm.
to realize this?
Yeah, I mean, in the context of infinite dimensional Hilbert spaces, in the last like 5-ish years, there are some papers that have actually realized this particular anomaly in those models. These are like rotor models with like a infinite dimensional rotor degree of freedom per site. I'll point out references to those along the way.
I see. Thank you.
Yeah. Okay. Other questions? Right. So let me first talk about the field theory. So the field theory is a pretty simple one. It involves a massless Dirac field. Um, you have a two-component vector where each component is a single component, so-called Weil fermion. Um, and the action is given by this expression right here, where the psi L and psi R are the left-moving and right-moving components of the Dirac field. Um, and you can convince yourself by looking at the equations of motion why these names are associated to these two components of the Dirac field. Um, what are the symmetries of this field theory? There's an independent number conservation for each for both the left and right moving modes. Those are, you could call them the U1 left and U1 right. And there's a charge conjugation symmetry as well, um, which acts on the U1 left in a non-trivial manner. So here's how the symmetries act. The psi left and the psi left gets multiplied by a phase um, uh, when acted on by the U1 left, and the charge conjugation of the left movers interchanges the psi L and psi L dagger. So it like interchanges particle and antiparticle, essentially. The same goes for the U1 right. It acts on the right movers only. And there are associated Noether charges which are conserved. Whenever you have a symmetry, there's an associated conserved charge, and those are given by this QL and QR. Um, from these left-moving and right-moving U1s, it's useful to define these vector and axial charges, which are just linear combinations of the left mover and right mover charges. You can see that the vector charge or the vector charge generates a U1 symmetry, which acts with the same phase on both the left and right movers, whereas the axial U1 acts with opposite charges um, on opposite phases on the left movers and the right movers. In this sense, U1 axial is a chiral symmetry because it acts differently on the left and right movers. Um, these two U1 actions are not independent. Their Z2 actions are actually identified, um, which you can see by plugging in theta equals pi in these expressions. So the global form or the global symmetry is the Z2 quotient of these two, the direct product of these two symmetries. Um, these two symmetries have a mixed anomaly in the sense that if we couple a background gauge field for one of them, let's say we couple a background field for U1 vector, the other symmetry, in this case U1 axial, is broken. This is the kind of phenomenon that Schwinger identified in his 1959 paper, maybe in a different language. And this comment is mostly for the experts. Like in modern terms, we think of anomalies as associated to an inflow theory. So for any anomaly, there's or any anomaly of internal symmetries, um, in some cases also space-time symmetries, there's an associated theory in one higher dimension, which kind of cures the anomaly of kind of a boundary theory. So you take your symmetry, you take your theory in some d dimensions, you try to couple a background field, you break gauge invariance for those background fields, but then that gauge invariance is cured by coupling to a bulk, which also has the opposite kind of breaking of gauge invariance. So in this particular case, the inflow action is this quantum spin Hall theory. It's an invertible topological field theory, which is given by this action right here. You can rewrite this in terms of the vector and axial gauge fields as this. Okay. So this anomaly is a so-called perturbative anomaly in the sense that it's captured by a Feynman diagram, namely this. So you couple in this particular case, I've chosen to represent this as coupling the theory to a vector gauge field. and then checking computing the current correlation function. In equations, this picture is represented as this. You're computing the divergence of this axial current, and you find that it's proportional to the field strength associated to this background field, which I've represented as F. This was most clearly stated in a paper that followed Schwinger's paper by 4 years later um, by Johnson. And alternatively, as Schwinger originally showed, um, this is also reflected in the equal time commutator of the current densities associated to these two symmetries. You take the um, time components. So this is this J mu. In J mu, you plug in mu equals the time component, and you look at the same time slice, and you look at two different spatial points, uh, and you take a commutator of the um, of the of these two quantities, and it turns out that it's proportional to this derivative of a delta function. So you get some kind of a contact term, um, meaning when x1 and x2 are far away, then it's just zero. But when x1 approaches x2, uh, there's some non-trivial contribution. And if you stare at this long enough, you realize that if you had a finite dimensional Hilbert space, such a commutator cannot be realized in such a Hilbert space. This is because in a finite dimensional Hilbert space, any commutator has a vanishing trace, but the right-hand side does not. Right-hand side is just a C number. So it's impossible to realize such a commutator in a finite dimensional Hilbert space, but this has been realized in on infinite dimensional Hilbert spaces. So like you have some kind of lattice model, either Euclidean space-time lattice or Hamiltonian spatial lattice. In various forms, all of these papers have kind of shown how a bosonic analog of this anomaly can be realized on the lattice. The caveat is that you have to use an infinite dimensional on-site Hilbert space. So Leogen, to answer your earlier question, these are kind of the papers that try to address that.
Thanks.
Yep. Okay, so given what we've seen so far, you might be, I may have kind of convinced you that you cannot realize this anomaly on the lattice. So in a finite dimensional lattice. So why am I even giving this talk? So we'll see that we can actually do even though we cannot like realize the Schwinger term exactly in a finite dimensional lattice. There's a close uh, a, a, a very close avatar of that is realized in a finite dimensional lattice, and um, that's what I'm going to talk about for the rest of this talk. So first, we'll try to identify the axial symmetry on the lattice, and then we'll talk about its anomaly. So the way we'll talk about the fermions on the lattice is by considering this kind of a tight binding Hamiltonian, where there are fermions on each side of an L-side chain. We'll consider periodic boundary conditions here for simplicity, but we can also deal with the anti-periodic case. We'll assume that L is even, and kind of the intuition for this is that in the continuum, the Dirac field has two components. So the central idea of this model is to try to put the two components, or kind of distribute the two components among the even and odd sides of the lattice. And this Hamiltonian often goes by the name of staggered fermions in the lattice fermion community. I should have added a citation here. This goes back to Banks, Kogut, and Susskind in the 70s. So I'll often refer to this Hamiltonian as staggered fermion. Okay. And this Hamiltonian obviously has a number conservation symmetry, which acts like multiplying a phase on the fermions, on the fermion creation and annihilation operators. So there's an associated charge for the symmetry, which I'm going to call QV, um, which is given by this expression here. Uh, this is essentially the lattice analog of the vector symmetry, which rotates both the left and right movers in the field theory with the same phase. Um, but the question is, does this Hamiltonian also have a lattice version of the axial U1 symmetry? Um, And to get to that, we'll use a decomposition into Majorana-Weil fermions or real fermions. Um, and let's see why this is the way to go. First, we recall from our definitions of the axial and vector charges that QA, which is QL minus QR, is nothing but QV conjugated by the charge conjugation of the right movers, which takes QR to minus QR. Um, so in order to find the lattice axial charge, we'll try to look for a lattice operator that flows to this CR in the IR limit and the low energy long wavelength kind of limit. And to do so, it's useful to split the complex fermion into two real components. I call them A and B. In particular, we'll focus on the right-handed guy because that's the one that's going to play an important role. Um, so CR, which takes psi r to psi r dagger, it acts on the A and B as A as shown here. It doesn't do anything to A, but it flips the sign of B. That's simply because the I gets conjugated when you act with CR. Okay, so we'll try to remember this going forward because this is going to be useful. So following this discussion, we'll also decompose the lattice complex fermions, Cj, into real fermions. And I'll define them like this here. And these A and Bs, they satisfy the usual Majorana fermion anti-commutation relations, which are shown here. And now we recall that the Hamiltonian, which was just a tight binding Hamiltonian for the Cs, the C fermions, it can be rewritten in terms of these Majorana variables like this, which you can kind of convince yourself after some quick algebra. It can be diagonalized by going to momentum space. Here, alpha is the momentum space or the momentum mode associated to A, and beta is the one associated to B. In momentum space, Majorana fermions have the property that alpha of minus k is the dagger of alpha k. Same with beta. So this is kind of just like a number operator for alpha. This is the number operator for beta. So the dispersion looks like this. It's just a sinusoidal dispersion. The momentum modes alpha and beta at k near 0. The low energy modes near here, and the low energy modes near k equals L over 2. They correspond to the left and right moving Majorana fermions in the continuum limit in the field theory. So AL and BL are sitting around here. AR and BR are sitting around here. And now if we look at how the chiral translation operator, TB, which shifts only the B fermions by one side, but not the A. If you look at how it acts on the momentum modes of these B fermions, it turns out that it acts by this phase here. And if we concentrate near the low energy modes, which are near k equals 0 and k equals L over 2, this phase takes the value +1 near the left movers and -1 near the right movers, which means that TB acts, sorry, that. So TB acts like the right moving charge conjugation, which flip the sign of Br, but not of Bl. So that's what this argument shows us. And a quick note is that the full lattice translation, it also acts in a kind of chiral way, but it acts as the fermion parity for the right mover, since it flips the sign of both A and B. But that will not play an important role here. Okay. So with this argument, we've now concluded that TB, this lattice chiral translation operator, it acts like the right moving charge conjugation in the IR limit and the low energy limit. So we can define this QA as TB QV TB inverse. So by conjugating the lattice vector charge in analogy with how the continuum symmetries act. And by doing this by doing this conjugation, we can see that since QV has this expression in terms of the Majorana fermions, QA is simply a translated version of that, meaning you just shift the index of B by 1. So the upshot is that you end up with QV and QA, which both commute with the Hamiltonian. QV, of course, commutes with the Hamiltonian. We already argued that QV is the usual number conservation symmetry. But since TB is also a symmetry of the Hamiltonian, when you conjugate QV by TB, this whole thing is also a symmetry of the Hamiltonian. And this QA was discussed in a couple of papers from the 90s and they derived it by connecting it to some integrability literature. We give slightly different derivation, but in the end, the charge is exactly the same. And this QA has several nice properties. Firstly, of course, as we discussed, it commutes with the Hamiltonian. It also has integer eigenvalues. And one way to see that is that QV, we already know, we know that this QV is just a number operator, which of course has integer eigenvalues, just counting, the number of occupancy levels for each fermion. And TB is a unitary transformation. So since a unitary transformation cannot change the spectrum of any operator, the spectrum of QA is identical to that of QV. In other words, the eigenvalues of QA are identical to those of QV, and hence they're integer valued. QA also acts in a locality preserving manner on the fermions. So if you look at if you conjugate, let's say A at J at site J by e to the I theta QA, this is the theta rotation of the axial charge. It mixes it only with the B fermion on a neighboring site. And the same with B. It also gets mixed up only with the A fermion on a neighboring site. So it acts in a locality preserving manner on the lattice fermions. You can from this you can also work out how it acts on the complex fermions, the CJ, by taking linear combinations. It is also a sum of mutually commuting terms. All of these terms, AJ, BJ plus 1 for all J, they commute with each other. And so when you exponentiate this, you can write this as a product of almost local terms, terms which only act non-trivially on two sites. Okay. So you could say that this axial U1 is an almost local symmetry, almost on-site symmetry, I'm sorry. In fact, by as we showed, since TB relates, since conjugation by TB relates QV and QA, um, and QV is fully on site, it tells you that there is a unitary transformation, namely TB, which makes this completely on site. So if you're familiar with the slogan of on site means anomaly free, it should tell you that this U1 axial is completely anomaly free. Okay. But there's a price to pay, and price to pay is that in contrast with the continuum discussion, the lattice axial and vector charges don't actually commute. So if you take these two expressions, these two expressions here, compute the commutator, you get something non-trivial. Okay. So what is the full structure? In fact, we find that um, if you take repeated commutators of QV and QA, you actually generate something known as the Onsager algebra. This is an algebra that was discovered by Onsager in his 1944 paper solving the 2D classical Ising model. And there he defined, he had a slightly different presentation of the charges, but for our purposes, we'll define these generators, Q sub n and G sub n, which are indexed by integers. And you can observe by looking at this that Q0 is nothing but QV, and Q1 is nothing but QA. And this full set of generators, there's 2L of them, L being the number of sites. This full set of 2L generators, they satisfy these commutation relations. So the G's all commute with each other, but the Q's among themselves and Q's and G's, they have this non-trivial algebraic structure. In particular, setting n equals 0 and m equals 1 in the first equation, you see that Q0, Q1 is some non-trivial operator. And in particular, it's not 0. And it turns out that for fixed order 1 n in the L going to infinity limit, this thermodynamic limit, the Q ends with odd n flow to the continuum axial charge, whereas the Q ends with even n flow to the vector charge of the field theory. And all of the GNs, they flow to 0. So this really intricate Onsager algebra in the thermodynamic limit simply reduces to the U1 vector and U1 axial symmetries of the continuum, which commute with each other. This discussion was also partially present in these earlier works, where they studied a bosonized model, like a spin model, and they also pointed out this Onsager algebra structure in a related model. Let's address. Yeah.
Sorry, can I ask a question?
Yes, please.
We go to the previous slide. Yeah, so because QV and QA do not commute, so we cannot label any state by two quantum numbers like V charge and H.
Right.
But because so U1V and U1A are they are not the phaseful symmetry. The phaseful symmetry is further quotient by Z2. So I would expect that if we take the mod 2 value of QV QA commutator, it is 0.
That's right.
So
actually, yeah. Thanks for bringing this up. Actually, the Z2 subgroups are identical, so you can
even on the lattice, and you can
even on the
check.
lattice. That's right.
Is there like a easy way to?
Yeah. I should have talked about this, but yeah, thank you for pointing this out. You can see it from this expression here. So set theta equals pi. These two terms are gone, and cosine theta is -1. So both A and B are both A and B get their signs flipped. And if you look at this term, this also does the same thing. So this is e to the, you're looking at e to the I pi times this thing. And this number is either +1 or -1. So e to the I pi times this number is just going to be e to the I pi, right? Okay, I'm kind of doing air math here, but uh, essentially the fermion parity associated to the vector charge simply, I think I showed it somewhere earlier. Yeah. So it acts like this, right? So you set theta equals pi here. It also gets a minus sign. In particular, the A and B components will also get a minus sign because of
So
this.
what you are showing here is just that this QB and QA with this pi in the front, they act as the same way on
That's right.
both real fermion components.
That's right. That's right.
Okay.
Yeah.
Okay. Yeah. Thank you.
Okay. Cool. Yeah. Yeah. Thanks for that question. Okay. Okay. So now that we've discussed this lattice axial charge, I want to address a potential complaint. So there's a famous theorem in the field of chiral fermions, which was first proposed by Nielsen and Enomiya, and then sharpened by Friedan's work. One of the sort of implications of this theorem is that any lattice axial charge that preserves locality, like our QA does, it cannot satisfy both of these two properties listed here. The first property is that its eigenvalues are integer quantized, and the second one is that it commutes with the vector charge. And the QA that we've discussed so far, it satisfies one but not two. But it turns out that one can construct a different axial charge, which I'll call Q tilde A, that satisfies two but not one. And this goes back to the work of Banks et al. In 1976. It's closely related to the QA, and in particular, if you remember the definitions of Qn, then Q tilde A is just Q1 plus Q minus 1 times 1/2. So in particular, because Q1 and Q minus 1 are both symmetries, Q1, the average of Q1 and Q minus 1 is also a symmetry of the Hamiltonian. So that's how one can construct Q tilde A. However, you see that the terms in Q tilde A, they don't commute with each other. And a related fact is that the eigenvalues of Q tilde A are not integer quantized. However, it commutes with the vector charge. Again, this is something you could work out from the Onzager algebra. You see that if you set n equals 0 and m equals either 1 or -1, those two commutators lead to the same operator up to an overall minus sign. So if you add those two, Q1 and Q minus 1, the commutator of that sum with Q0 vanishes. So in other words, Q tilde A does commute with the lattice vector charge. So in the end, what we find is that we can either satisfy one or the other, but not both. But both of these charges, and as we argued earlier or commented earlier, all of the QNs with odd n, they all flow to the continuum axial charge. So in some sense, they're all good axial charges. But there's a major difference between how these two charges act as symmetries on the operators of your theory. While QA, as I showed, acts in a locality preserving manner. Q tilde A, in fact, violates that. So if you exponentiate e to the, if you write e to the I theta Q tilde A and you conjugate a local fermion operator, a Cj, the result of that is a superposition over fermions, which have support on the entire lattice. So each fermion gets mapped to a sum of an extensively large number of fermion modes. So in that sense, you shouldn't like Q tilde A too much. Okay. Let me see if there are any questions before I move on to the anomaly matching discussion.
Can you explain what does this axial charge look like in the spring model on the Jodorowsky transformation?
I will mention that okay, maybe I can show it right. I will mention that at the end of the talk, if that's okay.
Thanks. Okay,
Yeah,
thanks.
I don't have the exact expression with me though, but let me comment on that at the end of the talk, if that's okay.
Okay, thanks.
Okay, cool. Thank you. Okay. Okay. Let me move on to discussing how the anomaly emerges from the lattice symmetry. To answer this question, we'll go to momentum space. We'll define the K space complex fermions. We'll call them gamma K. They're defined like so. And we rewrite our Hamiltonian and our symmetry charges in terms of these gamma K. They have these expressions, which the expressions themselves are not very important, but I want to highlight how these symmetries act near the low energy modes, which are, as we said, near k equals 0 and L over 2. QV acts like any usual number conservation operator, like so. But QA has this superposition over both the particle and whole creation operators. And in particular, if we focus near k equals 0 and k equals L over 2, the sine term dies, and the cosine becomes either +1 or -1, depending on whether k is near 0 or k is near L over 2. And these reflect the action of the axial and vector charges in the continuum, where QV acting on the psi dagger, both left and right, just gives you +1 times psi dagger left or right. Whereas the axial charge, it gives you a plus or minus sign, depending on whether it's a left mover or a right mover creation operator. And those correspond to k equals 0 and L over 2, as we discussed before. And so these plus or minus signs are exactly how the axial charge in the continuum acts on the fermion creation operators. Okay, so then kind of like the upshot of that is that in the IR limit, the QV and QA charges on the lattice, they act in an identical manner to the field theory or continuum vector and axial charges. So we say that the lattice symmetries flow to the continuum symmetries. And the mixed anomaly of the continuum symmetries, as indicated by either the bubble diagram or the Schwinger term, those things all emerge or emanate from the lattice vector and axial symmetries. But is there a way to see the anomaly on the lattice itself rather than have it kind of emerge in the IR? And to address this question, we'll use kind of a new definition of anomaly, which is inspired by research on generalized symmetries, which says that a global symmetry S is anomaly free if it allows a gapped, non-degenerate symmetric ground state. And this is related in many ways to the sort of obstruction to gauging definition of anomalies that may be more familiar in um, more familiar from invertible symmetries, but progress in non-invertible symmetries has kind of suggested that we should update that definition to this one here. It's more easily generalizable to non-invertible symmetries, but it's identical in the invertible case that we're all familiar with. This has been discussed in a lot of detail in this paper here, so I encourage the audience to check it out if they want to understand the connection between these two definitions. And one reason that this definition of an anomaly as an obstruction to gauging or coupling to a background field for the symmetry is not a good one for our lattice symmetry, is that the lattice symmetry here is this Onsager algebra, which has many charges that are extremely non-local. Remember, there's an index associated to the charges, and those indices go from anywhere from 1 to L, and in the large system size limit, that number could, some of the charges are highly non-local. So it's not clear what it means to couple a gauge field for those symmetries in the lattice model. So we claim here that it turns out that any QV and QA symmetric Hamiltonian is necessarily gapless, which is which kind of reflects the first definition here. So the claim is that this result here tells us that the lattice symmetry also has an anomaly. So that's how we kind of realize the anomaly on the lattice. And it turns out that, as I sort of alluded to along the way, both the vector and the axial symmetries, they're individually anomaly free. And that's reflected in the fact that it's possible to open an energy gap with deformations of the Hamiltonian that preserve either QV and break QA, or preserve QA and break QV. So really, the QV and QA, they seem to have there's a constraint that prevents us from opening a gap whenever both of those symmetries are preserved. I'll maybe quickly go over the sketch of the proof since I have time. So the first step in proving this is to note that the Z4 subgroups of this U1V and the U1A, their product acts identically as this kind of opposite translation operator, TB times TA inverse, TB and TA being the translation operators for the B and A fermions, respectively. So requiring invariance under both of these U1 symmetries implies TB times TA inverse invariance. And now if we impose this TB times TA inverse symmetry, it rules out any coupling between A and B, because if you keep applying this operator repeatedly, any such local coupling between A and B will become increasingly non-local. So if your Hamiltonian must be a sum of local terms, if you want a local Hamiltonian, you're essentially forbidden from coupling the A's and B's.
Question?
Yeah.
So what is the least non-local Hamiltonian that is compatible with this TBTA inverse? How non-local?
Yeah, maybe let me come to that in like 2 bullet points. Okay. So yeah, I'm getting there. So the next step is to ask what kind of couplings that are only between the A's and only between the B's are allowed. And it turns out that any quartic or higher order couplings would break the vector symmetry. And so the only allowed terms are of this form, where n is some finite order 1 number. N equals 1 corresponds to the term in our staggered fermion Hamiltonian. But you could choose any n as long as n is not large and n is not order L. So this is the kind, this is the these are the allowed Hamiltonian terms. And you see that the entire family of such Hamiltonians is gapless. Okay. Does this answer your question, Yojun?
Yes. So suppose I consider non-local Hamiltonians where the coupling decays in some, say, polynomial way as the distance between the degrees of freedom increases. Is it possible to open a gap?
So I think uh, in this case, I'm even allowing something more drastic, right? I'm allowing you to like couple. Um, sorry, let me think.
So my understanding is in point four, you have some upper limit of this little n, right? You
That's right. Yeah, I think I want in the large L large system size limit, I want um, the Hamiltonian to still remain local. So I want
yeah,
the N to be order one. Yeah.
yeah, I'm considering the case where it's non-local, but
That's an interesting question, actually. Uh-huh.
the interaction
Let me
is
see.
as in power law.
Right, right, right. Yeah, it's an interesting question, but let me see if I can answer that this way. So let's say your um, A and B fermions were coupled in some decaying manner as A and B go farther and farther away. But then if you act with this TBTA inverse, um, any term that was like strongly coupling A and B near each other under this transformation, it would now strongly couple A and B fermions very far away, right? So in some sense, like you don't actually require like non-decaying couplings. That makes sense. Like even if you had like a power law decaying coupling between A and B, um, re requiring this as a symmetry um, would kind of rule that out.
Is it the case? So if I look at point four, if the interaction is 1/n to some power, is that
Mhm.
symmetric?
Uh, So, oh, you mean you put the power out here, like
Yeah, so
the power does not rise.
I have some overall coefficient that's proportional to
Uh-huh.
1/n to some power, like 1/n squared.
Uh-huh.
Is that symmetric?
That's a good, I mean, I haven't thought about this. We only looked at um, Hamiltonians that were kind of like almost local in this sense.
Yeah.
But this is a good point. Yeah, I haven't
Yeah,
thought about this, to be honest.
previously with some other people, we proved a theorem for this kind of anomaly type constraint, even for non-local Hamiltonians.
I see, I see. Okay. Yeah, we should talk offline about that. Yeah, it's
Yeah,
an interesting
thanks.
point. Yeah.
Maybe related question. So
Uh,
suppose I just have a finite sized chain, and so I can regard it as a quantum mechanics problem. And
mhm.
then is it possible to have a unique ground state for
Um,
this symmetric Hamiltonian?
oh, yeah, I think in that case, like, in that case, it depends on the boundary conditions. For the periodic case, I think there's ground state degeneracy. But for the anti-periodic case, you always have a unique ground state. So when I say gapless here, what I really mean is I'm considering some thermodynamic limit where I define gaplessness as there being a finite order one gap between the ground state and the next excited state. But
Oh,
in like a finite system, yeah,
I'm
I think
just
you're asking me a
asking
finite
to
system.
I'm just asking to check if this is already an anomaly at 0 plus 1D, or is it
Mhm.
only an anomaly in 1 plus 1D?
I see.
Since the
So,
QV and
right.
QA do not commute, right?
That's right. That's true for any L. That's right. I'm not sure how I would define a gap in a 0+1D system. I mean,
I just mean degeneracy in
I
that
see.
case.
I mean, there's a degeneracy associated to the boundary condition, which maybe not what you're talking about. So
Okay, I see.
there's a boundary condition dependent degeneracy. Like if you had a periodic boundary condition, there would be some zero modes which would, you know, contribute to
Okay,
some degeneracy. But for the anti-periodic boundary condition,
I see. Okay,
you would get
thanks.
a unique ground state. Yeah.
I have another question. So
Yeah,
in this proof, I think you assume that the Hilbert space is just the Hilbert space of these A and B fermions.
that's right.
But in order to, like in general, when we say like some symmetry has implication of the phase, like we can rule out a trivially gapped phase or even gapped phase, we don't assume a specific Hilbert space, right? So we allow like adding many bosons to the Hilbert space, for example. So
Right. Right. Yeah, here you're right. I mean, here we are kind of using a restricted notion of like what it means to deform a model.
yeah,
So in general, I think you're definitely allowed to couple in ancillas. So this
yeah,
does not address that.
I see.
Right.
But we also believe that even if you are allowed to add further, like adding further degrees of freedom, then it's still uh, it can still not be gapped out while
Right.
preserving the symmetry.
Right. That's right. That's right.
But okay, I see.
Yeah, but
Thanks.
in the field theory, there's also, you know, there are terms that will break the vector, but not the axial, and you know, gap it out, and vice versa.
Yeah.
So yeah, it's kind of, so we're kind of asking whether that scenario is possible within this lattice map, within the same Hilbert space. Yeah, but that's a
Yes.
good point. Like, I think uh, you could ask, given this algebra, you know, given this algebraic structure, is there
Yeah.
any, you know, any Hilbert space or where you can write down a symmetric gapped ground state for these two symmetries with QV and
Yeah.
QA?
Yeah.
That's an
Right.
interesting question, and this does not address that question.
Yes. Oh, another
Yeah.
question is, so if I consider chiral symmetry, not the axial, but the chiral symmetry,
Mhm.
and I can still compute this. So first of all, chiral symmetry charge can be obtained from QA and QV by doing some like linear combination, right, with a
In the
fractional
continuum,
coefficient.
yeah. Uh-huh.
No, even in the lattice. Sorry,
Uh,
even yeah.
oh,
Let's
I see.
see.
You want to define Q.
That's my
Yeah.
guess. Yeah.
Uh-huh.
So is it? So
So you can
naively, I would
define it
take
for sure.
ah
Right. You
yes.
can define it for sure, but I think the problem is that such a QL and a QR would not have integer quantized eigenvalues. Right. So it has the same
So
problems as this tilde QA that I mentioned earlier. So in other words,
um
they wouldn't act locally for a finite lattice. But
oh
in some thermodynamic limit, they might they'll still approach the QL, QR.
sorry, what's the relation between acting locally and have integer eigenvalues?
Um, hmm. Yeah, maybe those are not related, but uh, those are both true for I think for
Uh-huh.
both QL and QR. Yeah, sorry. Maybe they're not related.
I see. But you see, but there's still a chiral version of the Schringer anomaly, namely like a Q chiral, Q left, Q a J left, a J left commutator is some
That's right.
delta function.
That's right. That's right.
And one can ask what is the lattice manifestation of that. But you say that's
That's right.
this defining Q, defining Q left is more challenging because this naive way does not give you integer eigenvalue property.
Right.
Property.
I think in other words, I want to say that Q, even if you define this Q left,
Yes.
because the eigenvalues are not integer quantized, e raised to I 2 pi times Q left will not be 1. So it won't be like a faithful representation of U1. Does that make sense? That's not a compact symmetry. It'll be more like an R symmetry.
I see. Okay.
But of course, in the continuum limit, like once you take this system size going to infinity limit, you will end up getting the continuum Q left, I think. Yeah.
So just to extend this discussion of only one of the two chiral modes, I think there's some argument based on the entanglement structure that says if we have a lattice system where the Hilbert space is a tensor product, then not even to mention this symmetry, just having a left or right moving thing is not allowed. Meaning just having a chiral central charge is not allowed, not even to mention the symmetry. It is based on some assumptions of the entanglement structure. The modular commutator has to take some form.
Yeah, I mean, in this case, I don't think there's, you don't have just a left mover or a right mover.
Yeah. I was talking
right.
about
So it's
what I was talking about what Yunqing was asking about. Yunqing was asking about the case where I think Yunqing was asking about the case where we only have left and right, or right.
Oh, I see.
Or is Yunqing asking about the case where we have both?
No. I'm asking about the theory is still non-chiral, but I'm asking whether we can realize the chiral symmetry in the non-chiral theory.
I see.
Like whether I can realize U1L charge on the lattice of a non-chiral lattice model, staggered fermion, for example.
Okay.
Yeah, but yeah.
Okay, good. Yeah.
It's a weaker question. Yeah.
Okay. So let me also make a quick comment about U1 axial being anomaly free. We claim that U1 axial is anomaly free according to this more general definition of allowing a symmetric gap non-degenerate ground state, but we can also illustrate it more explicitly by coupling in a gauge field for U1 axial, and we do this in the paper. I'm not going to go over this right now, but the gauged Hamiltonian kind of looks like this, and it's unitarily related to conventional Schwinger model for 1+1D lattice QED. So you gauge either U1 axial or U1 vector, you get a lattice model that represents like a lattice regularization for 1+1D QED. Okay, let me just conclude here because I'm out of time. So in this talk, we discussed how the symmetries of the massless direct fermion in 1+1D are realized exactly as exactly in the lattice Hamiltonian as U1 symmetries. And we discussed how the mixed anomaly of the continuum symmetries is matched by this non-abelian structure, namely the Zagar algebra. And we discussed how a gapless constraint emerges from this non-commuting structure of the symmetries. And it reflects and closely parallels the constraints arising from the anomaly in the continuum, which rules out symmetric gap opening deformations when you assume both QV and QA. Yeah, there are a few future directions. One direction is to consider non-abelian gauge fields. So we're thinking about 1+1D QCD with adjoint matter, where there are interesting non-invertible symmetries. The question is whether these symmetries survive on the lattice. There's also other perturbative so-called non-torsion anomalies, more complicated than this U1 times U1, even in 1+1D. They're signaled by various kinds of current commutation relations, morally similar to the Schwinger term. it'll be interesting to see if those can also be realized in the lattice. And let me quickly mention something about this bosonized version of the problem that was raised in the question. So this is some work that's still in progress. We show that if we bosonize the Hamiltonian, you get this get the XX model. This I shouldn't be here. This I shouldn't be here. You get the XX model or the isotropic XY model, as some people call it in the literature. And the IR limit of this Hamiltonian is the compact boson CFT. And the compact boson CFT has so-called momentum and winding symmetries. So those are the symmetries that these vector and axial charges will get mapped to under bosonization. And I do have the expression. Okay, I lied earlier. Sorry, this should have been W. That's my bad. This is the winding symmetry. So the bosonized version of the vector symmetry is this spin rotation symmetry, whereas the axial symmetry gets mapped to this kind of slightly more complicated looking charge. And these two are exact symmetries of the XX model. And indeed, they flow to the U1 symmetries of the CFT, which go by the name of momentum and winding. And we also realized a T duality, the T duality of the CFT, which sends R to 1 over R exactly on the lattice. And this is, we're still writing this up. So stay tuned if you want to know more about this. With that, I want to end my talk. Thank you for your attention.
Okay, thank you for the very interesting talk. Any other questions?
Oh, I have one more question, sir.
Yeah.
You mentioned about the graph degeneracy depend on the boundary condition, but isn't the U1 axial symmetry explicitly broken under anti-periodic boundary condition?
Yeah, that's a good question. The expression I wrote in on the slides, it had this kind of ambiguity where I didn't mention what BL plus 1 means. I wrote this AJ, BJ plus 1 and summed it from J equals 1 to L. But I didn't say what BL plus 1 means. It turns out that by just defining BL plus 1 as either plus 1 or minus 1, you actually get a symmetry of this
I see.
Hamiltonian for both boundary conditions. Yeah.
And also, do you happen to have examples of with both symmetries without translation invariance?
Yeah, both symmetries and translation, I don't think I have. Is there a reason why I should expect to not be the case? I don't think so, and I think it's because so yeah, it's because of this sorry. Yeah, it's because of this fact that requiring both U1V and U1A requires us to impose TB times TA inverse. But you see that TB and TA, once you've argued that A and B need to be decoupled, they're kind of completely decoupled, right? TB is just acting on the B's and TA is acting on the A. So this just means that you also have TB invariance and TA invariance. In other words, you end up with only translation invariant
I see.
Hamiltonians. Yeah. So I think that's
Okay.
yeah, that's kind of like the technical reason why. But yeah, if you generalize this as Yinchin was suggesting earlier to some general lattice Hamiltonian and some general Hilbert space with finite dimensional on-site factor, this does not have to be the case, right? I think yeah, there you can have something more general if you just require the kind of Onzager algebra symmetry.
Okay, thanks.
I also
thanks for that question.
just to make sure the QW in the last slide has integer valued eigenvalues. in the
That's right. That's right.
uh,
That's right.
and also here you are matching the anomaly in the sense that you show there is an anomaly in the sense there's obstruction to trivial state. You match precisely which anomaly it is.
So for the for this particular anomaly, there's only one non-trivial generator, right? So I guess you're asking like uh, which integer in the Z classification this is. Um,
I think this requires a definition of the integer index at the lattice level.
mhm, mhm. That's a really good question. I should say that I haven't thought about defining the index on the lattice. Um, I think that yeah, I think one difficulty is that the lattice symmetry is not the same as the continuum symmetry. So in usual contexts of anomaly matching, the symmetries in the continuum and the um, and the and in on the lattice, they match at least on some subgroup. And so then you can like kind of match the index associated to those subgroups. But here, because the U1, like the two U1s, they don't commute on the lattice. Yeah, I'm not sure whether one can. I mean, certainly you cannot define the index in the naive way, where you just treat the U1 vector and U1 axial as like independent U1s, couple engaged fields, and so on. You cannot do that because these are not like independent symmetries.
Yeah.
So yeah, you have to do something more clever to define an index, which I'm not sure how to do at this point.
Thanks. Any further questions?
Some technical things. So, throughout the talk, you assume that the number of lattice is even, right? L is even.
That's right.
Yeah. So I wonder, like, if L is odd, what kind of statement are remain the same, and what will change? For
So one
example, the
thing is that
Onsager algebra.
right.
Does the Onsager algebra
Yeah.
it
So
sounds like very local. Yeah.
mhm.
So,
Let me think. So one thing, well, one kind of naive thing is that the boundary conditions for the left movers and right movers will be different. Like one will have periodic, the other will have anti-periodic. With an even number of sites, both of them have the same boundary conditions. And maybe, yeah, one can, I guess, rephrase this as saying that odd number of sites is like inserting a defect in the fermion theory. Does that make sense?
yeah. Left the chiral fermion parity defect.
Right. That's right. Yeah. Yeah, you can see this from the fact that I argued earlier that translation, like the full translation TA times TB, is the chiral right moving parity operator. So yeah, that kind of tells you that if you add another site, it's like inserting a defect for that symmetry. But then I guess you're also asking like what happens to this like Onsager algebra structure.
Yeah.
Yeah, that's a really good question. Yeah, I don't have anything smart to say about that.
And then, yeah. So when we insert a defect, usually the symmetry operator will change, right? So it can be
That's right.
modified.
Yeah, you can, yeah.
And but I'm not quite sure about the charge. Uh, uh, like whether the charge operator will be modified or not. Whether there's a modification of the charge. So the, oh yeah, okay, presumably yes. So you expect that the charge is also modified, and then the answer algebra is also modified.
That's right. Yeah. There's something kind of morally similar to this in the bosonized story um where the let me think. So um there's a Z2 subgroup of the momentum which commutes with all of the winding. So if you insert a momentum defect, it ends up modifying the winding charge. It's not quite what you're asking for. I think you're asking for some like lattice translation defect, which is different. There is this internal symmetries.
Okay. Okay, yeah, okay, thanks.
Yeah, that's a good question. Yeah.
Any other questions? Okay, if not, let's conclude this seminar. Thank you, Aqua.
Okay. Yeah, thanks.
Yeah,
Thank you for
thanks.
sticking around to the end.
Yeah. So I will stop recording and then we can all leave.